Hey guys, so this is the test review for Unit 1 through 5. As I go through this, keep in mind, I may end up turning this into videos. It's a lot of questions to cover. I think we've got, 11 questions. It's going to be fairly long. If it does turn into 2 videos, make sure you watch both of them. If it doesn't turn into 2, just realize you can fast forward, rewind. I'm not going to go through what the question is, but we are going to talk about the concept and maybe do a practice problem. This should really line you up with how to take care of the test questions. And so the first question that we're dealing with is the ball on a string in a vertical circle. And so the premise is here, okay, we've got a ball on a string and we're going to spin it in a vertical circle, okay? The conceptual piece behind this is that the tension, the force of tension in the string pulling inward towards the middle is going to change as it goes around the circle. There are other forces acting on the ball. The only other force that we're really going to talk about, though, is the weight of the ball itself. And while it's very helpful at the top, the weight of the ball at the bottom actually opposes the force of tension. And if it were on the side, it would be a little bit more complicated. Because then, if we have weight pulling down and we're pulling in, right, then the ball's going to accelerate in a weird direction. It's not going to accelerate the way we might think. We actually end up having to pull up a little bit more so that the centripetal force is centered. That's not going to be where we're going to talk about our situation. We're going to talk either top or bottom of the circle, maybe both. But the concept is that the sum of the forces in the radial direction, okay, this weight and the tension on the ball, on the string, pulling on the ball, they have to total the cost of a circle. And the cost of traveling in a circle is mv squared over r. So no matter whether I give you a mass on a string at the top of a circle or the bottom of the circle, you've got to get a total that equals mv squared over r. So for instance, if I'm at the top, okay, sum of the forces at the top would equal force of tension, which is towards the center of the circle. I'm going to call the center of the circle positive, the outside of the circle negative. And because gravity is pointing in the same direction as I'm pulling with tension, I get to add those two forces to total up to mv squared over r. Now, let's talk about this. If it was at the bottom, the only difference here, math joke, is that it'd be subtraction instead of addition. You get the difference, right? Subtraction. Okay, at any rate, the thing is that if we did subtraction there or addition, it doesn't matter. What matters is what kinds of questions could I ask you about? Maybe I would ask you, how fast do you have to spin the ball to maintain a certain radius if you can only pull so hard? So if I give you the tension on the string and the mass of the ball and the size of the circle I want, yeah, it's fair for me to be able to ask you for one of these items. But I'm going to have to give you all the other items. So depending on which variable I'm asking you for, you should algebraically be able to solve it. The physics behind this is really the setup of this formula, understanding that these forces acting together have got to be mass times velocity squared over radius. That's the question. Now, if you need to go over a specific question with that, let's ask that on Teams or maybe in class together. Maybe this won't take too long. We'll go through this fairly quickly. Box on an incline with friction and without friction. So that means that if I put a box on an inclined plane, okay, we know there are certain forces that act on the box. Specifically, that gravity points down and the normal force points out off the surface. It's possible to have friction or to not have friction. We're going to deal with a non-friction problem to start with. What we do know is that if we put our y-axis in the direction of the normal force and our x-axis along the surface, okay, that mg can be broken into two things. It can be broken into mg cosine theta and mg sine of theta, where theta is this angle here. where we walked away with this was the understanding that the normal force will equal mg cosine of theta. Now that's always true for a surface where an object is sitting on the surface, not being lifted by a string or pulled by other people vertically. As long as all the weight is resting on the surface, yeah, the normal force will be mg cosine theta. But the sum of the forces in the x direction will equal, and if we look, there's only one force acting in the x direction. It is mg sine of theta. Okay? That is pushing us down the hill. So if there's nothing to oppose it, no friction to slow us down, that's the only force acting down the incline. Now, if there's no friction, we will assume this box will accelerate down the hill. It will move down the hill, which means the sum of the forces does not equal 0, but rather, like Newton said, the sum of the forces equals ma. Now, at this point, we can notice a couple of things. The mass in this problem is not significant to the question. This is something that's independent of mass. Gravity, that's a known factor. Theta could be a known factor, or it could be what I'm looking for. I have the right to ask for either of those. And the only other question in here is the acceleration. So I'm either going to share the theta with you and ask for acceleration, or I'm going to share the acceleration with you and ask for theta. But there's a direct relationship if friction's not included. Now, what happens when we do include friction? Let's look at the same picture and let's add friction in. Now, the box is going to tend to go down the hill, which means that the force of friction is going to be up the hill. The normal force isn't going to change. The formula for normal force will not change, but the sum of the forces in the x direction will. And we would have mg sine theta still going down the hill, but now we would have to subtract the force of friction. Now, this could equal 0. These could be balancing forces. We don't know. It's also possible that it goes down the hill, still accelerating down the hill. So we're going to say that this equals ma. Now, there is one special case I should make sure you're aware of. If, when you calculate, you find the acceleration to be up the hill, that it comes out negative acceleration, we have to understand the force of friction will never cause something to move. It will just try to stop something from moving. So let's say, for instance, that the force of friction was bigger than the force of gravity down the hill. If that's the case, then the object doesn't accelerate. It sits motionless on the hill. So if the numbers ever tell you that it's actually accelerating up the hill due to friction, it's wrong. You have to interpret the numbers and understand that result that way. All right? So that being said, there is one thing we're going to want to change in this. The mg sine theta, that's fine. Those are all things that we could calculate or look for. But it's minus the force of friction. We have a definition for the force of friction that's very useful. It's mu mg cosine theta. Now that mg cosine theta, remember, comes from the fact that the normal force is equal to mg cosine theta. And this equals ma. Again, the masses cancel. When you consider that gravity is a known value, theta is either going to be given to you or asked for, and what mu, the coefficient of friction, it's either got to be given or asked for, and then we have our acceleration. The only difference here is this introduction of mu. Okay, it makes the problem a little bit different, but it's not more challenging. Okay, but you should be able to answer this question with and without friction. All right, hopefully that helps. If you need to back that up to look at it for a little bit longer, you sure can. Let's take a look at question number 3. So question number 3 says the max speed on a banked turn with friction. Okay, this is a bonus question. Now in 20 and 21, I went through this and talked about how we're going to keep y straight up and x straight into the curve. So you have gravity straight down, you have the normal force pointed this way, but we're concerned with breaking the normal force into the two components. This would be Fn sine theta and Fn cosine theta. And so we could say that Fn cosine theta equals mg in this case. And we could say that Fn sine theta is pushing us into the turn, to keep us turning. However, if we include friction, there's another vector here, as friction is going to want to push down the hill. Which means that now we also have f of F, force of friction, times the sine of theta pointing down, and the force of friction cosine of theta pushing into the page, meaning that the sum of the forces in the y direction are Fn cosine theta minus mg and minus F force of friction times the sine of theta. And that will equal 0. We don't want the car to elevate vertically. The sum of the forces in the x direction would equal the Fn sine theta plus force of friction times the cosine of theta. And in order for this car to travel in a circular path, that must equal mv squared over r. Now listen, this is enough information to be able to solve it. And in the textbook, when I go through in 21 and 22 and I go through those problems, they're a doozy. And I take time to really process and validate how it works through substitution. The truth is, this is something that can also be sought out online. There is information out there, and I want to give you the right to go and search for that. You can seek out, how do I determine not what is the max velocity, but how do I find the max velocity on a banked turn? And there are formulas out there that will allow you to find that. I'll tell you one of the ones that I've seen before that I definitely trust, and I feel like I know for sure, I've seen plenty of times and I've used myself, involves a tangent. I'm not saying that it's the only option, but it's out there. Do some searching in terms of how do you find the max speed you can travel on a banked curve. It's an advanced problem, that's why it's a bonus, but I definitely want to give you that opportunity to do that if that's what you'd like. Question number 4, balancing force vectors. This is really simple. Okay? Let's say I have force vector A, force vector B, and force vector C. And I want this to be a balanced, non-moving object. Maybe this is a tree. You can imagine it being a tree. It's got all of its branches going every which way. And I don't want the tree to lean one way or the other. So while there's the wind, I also want to make sure that I've got these straps that are going to hold it upright in the right positions with the right amount of tension to keep it growing vertically and not bending in the wind. And so I've got these 3 different vectors of force being applied to it, and I want to make sure that it's stationary. And so what I have to do is I have to break each of these into their x and y components. So if you can imagine with me, there's an xy coordinate plane, and I'm going to break each of these into those components. Now notice FB is completely in the x direction. Okay, so let's say this is 3,600 newtons, and this is 500 newtons, and this is an unknown. I don't know how big FC has to be. Well, if I break FA into its x and y components based on the theta that exists here, with my angle, then I can sum up my forces in the x direction, and I can sum up my forces in the y direction. At the end of the day, this is a trigonometry, a basic trig problem mixed with a little Pythagorean theorem. I need the sums to be 0 if I want to hold something stationary in place. So whatever happens down here with FC, it's about getting balance and getting to 0. I want 0 force total acting on the tree. So keep that in mind as you break it down. But it's about breaking it into its x and y components and using a little trigonometry to do that. If you're not sure how to do that, come talk to me But just as a little heads up, this right here, okay, this side would be the opposite side, so that'd be a sine. It'd be like FA times the sine of theta, and so on. Depending on how you draw your triangles, the sine and cosine can flip-flop, but you still end up with the same basic number. Okay? Okay, let's leave that and talk about question 6 and so on. Or I guess we're on 5 now. Sorry, I get a little distracted. I'm not very good at erasing with my mouse. Oh well. Alright, we're just going to grab it all. Okay, so when we look at question number 5, it says that we're talking about a projectile launched at an angle. So I've got a projectile, and I'm going to launch it at, say, an angle theta. Okay, I might want to know how far is it going to go, or how long is it in the air? Questions like that. Questions that are all about our x and y components of projectile motion of our kinematics. V naught in the x direction, v in the x direction, a in the x, delta x, and t. We are v naught in the y direction, vy, ay, delta y, and t. So there's all of my information. Couple things. The vx is always the same. It's always constant because the acceleration is 0. So this information really doesn't help that much. All I really have is this. And if you look at the second kinematic, it says delta x equals v naught t plus 1/2 at squared. And because the acceleration is 0 over here, this is the only equation you can use on the x side of projectile motion. Over here on the y side, however, we do have some more information. We know that ay will be 9.8. Now, because I'm launching this somewhat upward, I'm going to call that a negative 9.8 meters per second squared. And then the rest of this gets a little bit wishy-washy, depending on where you are in the path of the object when I ask you for a question. If I ask for, say, the max height, that'd be delta y. At that point, the y component of the velocity would be 0. So Vy I could call 0, and that would help me solve it. If I ask for how far away does it land, that'd be delta x. And at that point, okay, Vy would be the negative of the initial y velocity. So whatever v naught y is, I'm going to hit the ground with that same y but in the negative direction, because I go up slowing down, and then as I come down I'm speeding up on my downward. Also, my delta y would technically be 0. The height change from the beginning to the end would be 0 if it's launched from the ground and hits the ground. So there's some information that we can really pull from that that might be really helpful. But at the end of the day, the biggest issue you're going to have is figuring out v naught in the y direction and v naught in the x direction. To do that, we're going to have to multiply a sine and a cosine if we know the initial velocity. So let's assume the initial velocity was like 16 meters per second and the angle was 13 degrees. Okay? Then v naught x would equal 16 times the cosine of 13. And v naught y would 16 times the sine of 13. So that's how we would calculate those two initial velocities, which we could then use over here in order to solve the kinematics, okay? I'm moving around a lot. I don't know why, but I'm pretty excited. Okay, let's look at, I'm sorry. Oh, man, long day. Number 6 is Kepler's third law. Kepler's third law, remember, we just learned about it, is T1 over T2 squared equals R1 over R2 cubed. And we're just going to do a really simple basic idea. You need to reference two different objects. It could be the Earth and then a planet. It could be a moon and a satellite. We have to compare two things that are orbiting the same thing. So an example of that would be like Neptune and the Earth. If I wanted to know how long it takes Neptune to get around the Earth, around the Sun, I would take the time of Neptune divided by the time of Earth, which would be 1 year. And Neptune's out farther than we are, so I certainly wouldn't use days. I'd probably use years. If you're close to us, like Mars, maybe I would do in days. but I probably still kind of look at years. If I don't like years when I'm done with this number, I can change it into something else by multiplication. Equals, now I need to know the radius of Neptune's orbit. Okay, that would have to be given in the question, or I'd have to give you access to finding that question. Whether that's in the book or being maybe looking online. I'd have to give you access to that information if I don't give it to you right away. And then I'd look at the radius of the Earth's orbit as it orbits around the sun. Now that's in our useful charts or other useful information. I think it's 1.5 E11, I think is the right number, and that's cubed. To solve something like this, we've got to remove exponents. So whether we're finding the radius or we're finding the time, we move this back and forth to be able to solve. But that's how we're going to set up Kepler's third law. Always have a comparison to be able to figure it out. Okay, I'm going to stop the video right here, and then I'm going to pick up with 7 through 11 in a second half video. All right.